In the second video, I will be going over the detailed calculations within the MIDAS design function and how it compares to my hand calculations. So, back to code check, column checking. Want to see the detailed calculations, we just click detail. First, let's just make it back to kip feet, and now we can take a look at it. Number, column, detail. Here, I'll show you here, and we'll go over exactly what it's doing here. First, we'll just give you your input parameters, and then I'll start first by calculating the slenderness ratio. I guess in this first section, I'll just quickly go over the slenderness ratio per ASHTO and what exactly it is doing. Here, we see that it is first calculating the ratio, and ASHTO says that if the ratio is less than 22, slenderness can be neglected, and if it is between 22 and 100, then the approximate evaluation of slenderness can be used, which is what MIDAS uses. This is why it was important to use our effective length factor to define it earlier. Now we will see the calculations will show this. So let's go over this quickly. In order to calculate this ratio, we need a few things. We just need our radius of gyration, which is first calculated by defining the area of the section and the moment of inertia. And then we get our radius of gyration. The program as well, 0.75 feet, 0.75 feet. So clearly, the slenderness ratio is both 40 in both. So the program says it is slender. The spreadsheet also says the approximate evaluation of slenderness can be used. For this approximate evaluation, ASHTO says you can either use the flexural stiffness of these two equations, the higher value of these two equations. However, this is where it differs a little bit from the program because the program only conservatively takes into account the concrete one. The flexural stiffness equation that only takes into account concrete and not the rebar. If you do want to calculate the rebar, I have also provided a quick example here. What I like to do is calculate the moment of inertia of the concrete, and then of the longitudinal reinforcement, I like to get it from CAD. It's just a little bit easier, but you can also just do your parallel axis theorem and manually calculate it like that. And this is why it was initially also important to define the permanent moments versus the total moment, because now for the flexural stiffness, we will be using the permanent over total ratio in both equations. So let's just compare our results with MIDAS. Here, let's just skip this CM factor for now, because we will be switching it, and I'll be showing you why. So we did the beta factor, right? MU permanent over total, 0.2857, same thing, 0.286, just round it up. And then for our flexural stiffness, like I mentioned, they only use the concrete one, but luckily in this case it is governing, so it does match, 648387, 648387. Okay? We will be using this flexural stiffness in our buckling load. Now when we go to our buckling load, which is calculated next, we'll see that it's 7,000 kips. In our spreadsheet, it is also 7,000 kips here. And what this buckling load is used, it is used in the deformation equations. And here is what we will have to update because our CM values in my spreadsheet and in MIDAS, they're a little bit different. So this CM value, I put it as 1 because the code says that conservatively for all other cases, you can just use 1. MIDAS default value is 0.85, so we do want to update this. And I'll quickly show you how we update this. Let's just exit out the report. We'll go back, we'll click close, and we go to common parameters, equivalent moment correction factor. And let's make this 1 in both directions. Select our column and click apply. Checking member. Detail. Now we should be getting the same deformation value. We were just doing this one first, so it should be 1.23. 1.23 as well. And here is also where MIDAS requires manual input for deformation of the sustained loads. Astro says for the CM value, we can also just make it 1. So technically they're both the same. In MIDAS, this requires an input. So what I like to do is I always run it, get the 1.23, and then input this value in the other deformation equation. And before I move on and show you how we do that, I also want to just grab the other direction so we can just do both at the same time. So it was 2.04 in the other direction. And we'll update this to 2.04 and this one to 1.23. And this is how we do it. And it's always in common parameters. Moment magnifier. Let's just change them to 1.23, 2.04. Just put both, 1.23, 2.04. Select and click apply. Run it. Checking. And you see now it's actually not passing. So that is why I wanted to show these detailed calculations, because we will have to increase the reinforcement. Click detail. Calculations. We're first doing this axis. So 1.23 in both directions. Now it matches 1.23, 1.23. Now we can finally calculate our magnified moment, which should be 344. Let's compare it with here. We have our no side sway moment, our side sway moment, and then our magnified moment equation, which matches 344 kip feet. What it does next, it just does it in the other direction, and I'll quickly show that as well. So longitudinal direction, sure it's the same. Calculate our slenderness effect again first. If it's slender, 70, 70, yes. We can use the approximate evaluation. We'll move on to get our beta, 0.43, 0.143. The permanent loads over the total load. Next, we'll move on to our flexural stiffness. We have a governing of 729,435. Flexural stiffness here, 429,435. It is okay. Then we'll just go down a little bit over here to our buckling load, 2611, 2611 kips. And since now we had changed our CM factor, they're both correct, we can just take a look at our deformation equation, 2.043, 2.043 in both directions. Let's just check our magnified moment, 100 node side sway moment of 600 kip feet, and then our magnified moment of 1428 kip feet. And we see why this magnified moment really was increased by so much because of these factors. So that is why it is not passing. And then here it will show all our calculations that are used for the summary report. And as you can see here in the interaction diagram, it's just not acceptable. First do your interaction equation. Then it will calculate your shear capacity here. And these are all just per Astro, so I will not show these calculations because the equations are shown here as well. We have shear strength of concrete, our maximum spacing of ties, and then our shear strength of reinforcement, and then our total shear strength, which we didn't have any, so it's okay. And that is the total calculation. It does have a minimum longitudinal reinforcement by shear check as well. So just quickly go back to our graphic and report, and we see that it's not good anymore. It is plotted outside of our interaction diagram. So when this is the case, we can do the following things. And column section data for checking. Let's click on this, and we could either use bigger rebar or more rebar. Say 14, number 10. Let's just try that first. Gotta replace. I'm checking. Here's a quick summary, so it is still not okay. The ratio here is 1.04, so it's almost. So let's just add a few more rebar. Go check, column checking. Not okay. Let's see what is showing. Look at it here. Oof, it is very, very close. It's the axial load. row check, column checking. Now it is okay. Here's a summary. Click on our member graphic. Finally, here we have our design. It is a little too close to 1, so I would probably add more rebar or some higher strength bars. And here it's plotted. It is exactly almost on the curve. That is how we do a column design. Thank you.